So f and g are inverse functions to each other if f composed with g of x equals x and ps g composed with f of x is also equal to x. So it has that property. It has further properties though. The functions are, now I'm going to write them down and then we'll discover them, okay, explore them. So don't stress about not knowing what it means. 1 to 1. The functions are 1 to 1. And when graphed, they are two words, I suppose, you could use: symmetrical or reflected about the line y equals x. And we saw that yesterday, the y equals x thing, how it was a mirror across y equals x. And we have looked, how to put this? We looked informally on how, I'll say that again. We looked informally about how to work out what the inverse function is, but in this lesson, we'll have a more formal way of doing it, and it will make a lot of sense. So, a quick explore. So, one-to-one functions. Here is an example of a function that is not one-to-one. One-to-one means that for any given input, there is well, how do I put this? For every output, there is only one input. That's probably a better way of looking at it, right? So, for example, the output of 1, let's make it 4. The output of 4 is found on this graph when I input 2. Yes? This is f of x equals x squared. But the output of 4 is also found when I input negative 2. So for two different inputs, for two different x values, there is the same output value. Now that's still properly a function, but it is not a one-to-one function. There are two inputs that go to the same output, and so it's a many-to-one function. Okay, there are many values, in this case just 2, but 2, basically the counting system for this kind of thing is easy. It's 1 and then many. So many, more than one, many inputs go to one output. So it's a function, but it's not a one-to-one function. Is that okay? For a cubic like this, that is a one-to-one function. So if I look at the value, I might zoom out a little bit, value 8 is found, come on, that could be helpful if I knew what I was doing. 8 is found when I input 2, because 2 cubed is 8, right? But if I go to negative 2, for example, negative 2 cubed is actually negative 8. So for a cubic, it actually is unique. So for every input here, there is a unique output. For every output, there is a unique input. So it's a one-to-one function. What do you think? Does that conceptually make sense to you? That's what one-to-one means. Okay. what test, when it comes to functions, what test did we apply? What's the difference between a relation and a function? The vertical line test. So here is the vertical line here. Can't quite see it because I've made it a bit paler, but the vertical line test, this is definitely a function. If I move this along, it only cuts, for any given point, it only cuts through the graph once. This is what makes it a function. For it to be one-to-one, it not only has to pass the vertical line test, but it also has to pass the horizontal line test. This function, as you can see, does not pass the horizontal line test. Am I making sense? If I look at a cubic, whoops, try that one again. If I look at a cubic, it passes the horizontal line test. Okay, so an inverse function passes, well, for a function to have an inverse, it must pass a vertical and horizontal line test. Oh, just for the video, I'll just say that I wrote passes the horizontal line test here. So if I look at the f of x equals x squared here, if I now look at its inverse, and don't worry about how I worked it out, we'll look at it in a second, but it might make sense to you anyway. We can see that its inverse here, although it exists, it's not a function, right? It's a relation. It's a relation. So the inverse exists, strictly speaking, but the inverse function does not exist because it fails the vertical line test in this instance. So if I pop this on, we can see that the dotted line, the inverse, fails the vertical line test. Now what we can do to fix it is, and I don't think this is in the course, so I'm just telling you this just because otherwise it doesn't make a lot of sense, I believe. If I set a restriction on the domain so that the original function does pass the horizontal line test, then its reflection will also exist as an inverse function. So in other words, although f of x equals x squared for all x does not exist, f of x equals x squared for x bigger than or equal to 0, that does exist. They're not the same function because I have restricted the domain to a smaller set of numbers, just all positive numbers and 0. Does that make sense? So if I do that, then it's a relation, because if I do the same thing here, except I'm flipping the domain and the range over, then you can see that the domain now works nicely. Sorry, that the function and its inverse are now passing vertical and horizontal line tests as much as you want. Okay? So I chose that to be less than or equal to 0, greater than or equal to 0. I could have made it less than or equal to 0, as long as I make this match up here. There we go. That is also a reflection. Now, I'll keep on talking about reflections and inverses and so on. What I might do now is I might just introduce our line of symmetry here so you can sort of see it. So again, it's very hard with doing this without it being 3D. But if you could imagine this, pulling this out of the page and flipping it over this line, it would pull out and then rest on the dotted line here. Yeah, so it's a mirror across this vertical line here. Okay, so typically, if you are restricting a function, it's normally to the right, so it's normally in a positive direction. So I'll put it back, but there's nothing stopping you from doing it the other way around. So we can see here, there's this line here. If I flip it across this line, this bit will flip over to there. The bit underneath the dotted line would flip over here, and the bit above the dotted line would flip over here as well. So we've got this flip happening. Okay, I can do the same thing with a cubic. I don't need to restrict the domain of a cubic. So there's the original function here, like so, and the flip is across here, like so. So it's good if you sort of take it in little bits. So this bit of the original function is flipped over to here. This bit of the original function is flipped over here. And this bit of the original function gets flipped. This bit here gets flipped, alley-oop, and comes down here, like so. So that's how it all works. And you can see that the cubic does not need to be restricted at all. Its inverse 100% passes the vertical line test because its original function, the original function, which is this one, passed the horizontal line test. Okay, so I'll summarize that because I spoke a fair bit there. The reason why the original function has to pass the horizontal line test is because when you flip it to its inverse, the horizontal line will become a vertical line. So it makes sure that the inverse is a function as well. If it fails the horizontal line test, then when you flip it, just get rid of all the extraneous detail. When you flip it, if it fails the horizontal line test in the original graph, then when you flip it, it would be a relation and not a function. All right, anyone got any questions about that? So, oh yes, Florence, go. Yep. So I won't wait for you though. A couple of things to note. I'm not putting them in the notes, so they'll only be found in the video. Number one, whether it's a relation or a function, where it does pass through the y equals x, the points of intersection of the inverse and of the function and its, sorry, I'm being all tongue-tied. When you look at the function and its inverse, the points of intersection, i.e. where they overlap, are always going to be on the line y equals x because of the symmetrical property of them. So they lie on here and here. The second thing, which I mentioned last time, but I'm just going to mention again, and ignore the fact that this is a relation, not a function, doesn't matter for what we're doing here, that when we have an inverse, excuse me, effectively what we're doing is we're flipping the domain and the range. So the inverse's domain is the same as the original function's range, and the inverse's range is the same as the original function's domain. Okay, so what does that all mean? It means that on the inverse, I've got 4, 2, and on the original function, I've got 2, 4. And that's true for every point. Let me just pick one like here. This is 2.244 and 5.0366. And 5 point, maybe I shouldn't have done that. No, I'm not going to get exactly. You can see approximately here. This is 5.06 and 2.25 here. So all you're doing realistically when you've got a function and its inverse is you're flipping the x and the y values. Okay. Questions? All righty, a bit more notes. I'll zoom out so you can sort of see a bit more. So notation, the inverse of f of x is written as follows. F to the minus 1 of x. Just that, okay? So if how you would say that is f inverse of x. F inverse of x. You wouldn't say f to the minus 1, you just say f inverse of x. Or you might say the inverse of f of x if you're describing it in general. But normally it's f inverse of x equals something. Okay, I'm going to go through a few examples now, and you'll see that it's not too hard working out the inverse. Inverses do get more complex, but they're outside the SL course, so that's easy enough. PS, you'll also come across functions that you haven't seen before, like the square root function and stuff like that. That's okay. You just need to know how to create the inverse function, not necessarily how to graph it without technology. So example 1 here is f of x equals 2x plus 1. So what I'm going to do first of all is I'm going to write this with a y instead of an f of x. So now, instead of talking about the function, I'm talking about the coordinate y is given by multiplying the x coordinate by 2 and adding 1 to it. And you remember what I said before? I said that for an inverse function, all we're really doing is we're flipping the x and the y coordinates, right? So guess what we're going to do now? Flip the x and the y. So the next line is x is equal to 2y plus 1. And now you work out what y is equal to. I'll give you 30 seconds to see if you can get ahead of me, or pause the video if you're watching this back. Okay. So hopefully that wasn't too challenging for you. I'm going to put the 2y on this side, but what I'm going to do effectively is I'm going to subtract 1 from both sides. Oh, yeah. Okay, so we've got 2y equals x minus 1 by subtracting 1 from both sides. And then I'm going to divide both sides by 2. So I get y is equal to x minus 1 on 2. And if you got that, that's fine. It might be argued that it's slightly better to have it as a half x minus a half, because then it's like a gradient of a half and a y-intercept of minus a half. So it's clearer in terms of the mx plus c notation, arguably. That's what you've got as your rule, which you then just write f inverse 1 of x. So f inverse of x is equal to, and you write that down. So a half of x minus a half is the function. But if you write x minus 1 on 2, that'd be fine as well. It's no biggie, one way or the other. Okay, any questions on that? Is that pretty straightforward? Okay, see if you can get ahead of me again with example 2. F of x is equal to 2x squared. So you're going to set f of x equal to y, and you are going to solve for x. Easy, come here. So, first of all, I'll talk it through. Y is equal to 2x squared. Switch the inputs and the outputs. X is equal to 2y squared. And then we solve for y. So divide both sides by 2. And then I'm going to flip the y to the other side and take the square root of both sides. So y is equal to the square root of x on 2. And that is the function. Now, team, question. Depends on how good your algebra from past years is, really. Normally, when we take the square root of something with a variable, we go plus or minus. Why don't I plus or minus it this time? Why have I just gone square root of x on 2, which is effectively the positive square root? Not just 1-to-1, Maddie, but you're 100% on the right track. Not just 1-to-1. If I said y equals plus or minus root x on 2, not only would it not be 1-to-1, it wouldn't be a function. Yeah? Because what I'm saying, if I put a plus or minus in there, I'm saying that when x equals, let's just say when I say x equals 4, when x equals 4, when x equals 8, 8 divided by 2 is 4. If I had a plus or minus there, I'd be saying plus or minus 2. Okay, when x equals 8, y would equal plus or minus 2. And that immediately means that it is not a function. Okay, so when I take the square root of it, I very deliberately only take the positive square root of it so that it works as a relation. So it works as a function. So when I say note the domain and range here, we can note this only works if we restrict the domain of f of x. Oh, that's really small. Sorry. I'm going to zoom that up so you can see it a little bit better. So this only works if we restrict the domain of f of x. So if we make the domain of f from 0 to infinity, then because when we flip it, we're flipping the x and the y's, the range will be 0 to infinity and we'll be fine. We will be fine. And I didn't write this down, but if I restrict the domain of f to 0 to infinity, then the range of f will be 0 to infinity. And then the domain of f inverse will also be 0 to infinity. Again, I'll just show you that visually. But again, I think doing this sort of restriction is a little bit outside the course. I think pretty well much, I think this is true, that any restrictions will be taken care of already. So if you're given a question in the exam, you might be told to find the inverse of f of x equals 2x squared, but after it will say, comma, x greater than or equal to 0. So that's the restriction. They're saying that, does that kind of make sense? So I know you won't be asked to find the restriction. F of x equals 2x squared, what domain would work for the inverse to exist? You won't be asked that. But just so you know, when it says f of x equals 2x squared, comma, x greater than or equal to 0, that's what it's doing. It's restricting the domain so everything else, so the inverse exists. So back to here for a seckie. So the domain at the moment is all real x, and the range is all positive x, all positive y, and 0 for the red one. Get rid of the extraneous detail so you can see it. Okay, so by restricting it, we change the domain so that it is now all real x as long as x is greater than or equal to 0. In other words, from 0 to infinity. The range is also from 0 to infinity. And the inverse, and you can see what I've done now with my inverse. I literally just switched the y and the x coordinates by doing that. And the inverse is, ignore this bit here. The inverse function is now going to be all real x from 0 to infinity. And also the domain, I'll say that again. The domain is going to be all real x from 0 to infinity, and the range is going to be all real y from 0 to infinity. It's moving quite slowly, but it is going to go to infinity as we go further up. Okay, so that's basically that. And again, put the symmetry line in so that we can see the points of intersection will be on the line, which is kind of handy because it's pretty easy then to work out what those points of intersection are. Okay, I've got a third example, and then you're going to have some work to do. And again, I'll do the same thing, I think. And that is, I'm going to get you to, I'm going to get you to take the example, f of x equals x on x minus 1, and I'll give you a chance to do it yourself. I want you to work your way through to work out what the inverse function is. I'll give you a minute to do that. Okay, so I'm going to multiply both sides by x minus 1 in order to get rid of the fraction. Whenever we can, we've got to try and get rid of those fractions. So that'll give me y outside of x minus 1 is equal to, oh, sorry, my bad. Blip, 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 blip. Wish I hadn't started recording. Of course, the first step is to switcheroo the x's and the y's. Now I'll multiply both sides by y minus 1 to get x outside of y minus 1 is equal to y. Now I can then expand that to get xy minus x is equal to y. And it kind of feels like we've done our job, right? In that we've got a y by itself on the right-hand side, and then we've got an expression on the left. So the expression on the left must be the inverse function. But that's not enough yet, because if you've got a y in both, y only needs to exist in one spot only. If it exists in more than one spot, you've got to keep working. So I'll give you the next line, or the next couple of lines, and then I'll see if you can finish it off. If I subtract y from both sides and add x to both sides, I'll get xy minus y on the left, and I'll get x on the right. I'll pause the video here. Next step is I've got a common factor of y here, so I can do that, which is good, because now I should be able to move on to the conclusion. Give everyone a second to do that. So we're dividing both sides by by x minus 1, and we'll get y equals x over x minus 1, i.e. f inverse of x is equal to x over x minus 1. And what do you notice about that? The same as the OG function, isn't it? So we call that kind of function self-invertible. Have you finished with my notes? Cool. I want to make sure I get my language right from my notes. Okay, so this is just a bit of language you need to know. When this happens, f of x is called a self-inverse function. Oh, serious shush. It's called a self-inverse function, i.e. f composed with f of x is equal to x. F of x is equal to x. And I've got no real way of showing you this easily, but if I just really quickly turn off these ones and put in, this is what f of x equals x over x minus 1 looks like. It looks like that. So if you can imagine flipping over the y equals x, this bit would flip over to here, and this bit would flip over to here. And so when you flipped it, it'll look, that's not true. Say that again. This bit would actually just flip so that this bit is down here and this bit is up here. Similarly over here, this bit would flip to there and this bit would flip to be up there. So when you flip it, it would actually just be exactly in the same spot effectively. So it's a self-inverse function. So there you go. So what you're going to do now, as you can see, is exercise 3F from your textbook. It starts on page 89. I want you to know that a lot of these graph types are ones that you haven't seen before. That's okay, it doesn't matter. However, I'm just trying to think. I should have looked at these a bit more carefully before because some of them are a bit more full on than we need really right now. We're going to continue looking at inverses and composite functions as we go on. This is just supposed to be a general look at them. Probably start with, so start with question 1, but don't worry about where it says graphing y equals x, y equals f of x, and so on. Just find, for each of a and b here, and a, b, and c here, just find the inverse. Okay, don't worry about anything else. Just find the inverse for these ones. And then you can do question 3 onwards. Some of them might be outside well, they were definitely inside the course, but maybe outside what you can do right now. But I think generally speaking, you should be right. Okay, so questions 1 and 2, just find the inverse. And then question 3 onwards, see how you go with it. Yeah. So question 1 and question 2, just find the inverse. And then question 3 onwards. Sure.